So the purpose of this phase locking demo is to show how to work with complex data sets. And I'm going to show this by computing intertrial phase locking in an SSVEP paradigm. We're going to use this SSVEP dataset, which is a recording of a participant passively viewing a reversing checker pattern. In this recording, there are 40 epochs in which the pattern reversal has occurred at a 6 Hz frequency and another 40 at 15 Hz frequency. And here the bin 2 epochs represent the 15 Hz trials and bin 1 the 6 Hz trials. And there's already been some basic pre-processing on this dataset as well. But just a common average, we reference a bandpass from 0.1 to 60 Hz, and each trial has been epoched from -5 seconds to 15 seconds relative to the trial start time, with the stimulus in each trial lasting a total of 10 seconds. Oh, and you'll notice also that the blink artifacts have already been removed. Now, I don't know if anyone would ever actually want to calculate intertrial phase locking on an SSVEP recording, but this will serve as a good example for this, since viewing a flickering stimulus will drive an oscillation in the striate cortex of that same frequency. And if the stimulus flickers at the same phase each trial, then the SSVEP should also maintain the same phase at each trial. So we should get fairly strong phase locking values from this signal. Quickly though, I'm going to give an overview of how we're actually going to calculate this, since it will require a few different steps. Of course, intertrial phase locking is a measure of how similar the phase at a particular frequency is across multiple trials at a given time point. If you're not already familiar with this though, there are much better sources for understanding it than this. I doubt that I'm going to explain it here in a way that will make much sense to anyone that isn't already familiar with the measurement. This is really just to serve as a reminder. How we'll measure this here is by first convolving the signal at a particular frequency and collecting the complex output signal. Then, in all 6 Hz trials, for example, we'll collect the complex vectors at a particular time point in each trial. And let's say that this is a plot of all the complex vectors collected at the 100 millisecond time point in each trial. In reality, there would be much more, obviously. The angles that these vectors form are the phase of the oscillation, and the magnitude of each vector is the amplitude of that oscillation. While intertrial phase locking is just the measure of how tightly grouped these phase vectors are. And you can see that these are not tightly grouped at all, they're pretty spread out across the circle, and so we should not get a high phase locking value. So the first thing we'll do is normalize each vector to be of unit length. And so with that, we've lost all the amplitude and power from the signal. And then we'll average all these real and imaginary vector components to form a single averaged vector, and you can see that here in red. The magnitude of this averaged vector is the phase locking value. It is fairly low here, like we predicted, since the phase vectors are not tightly grouped together. But for example, if they were more tightly grouped, we'd get a larger phase locking value, such as you can see here. So if all the phases are identical, the phase locking value would be equal to 1, and if they were all perfectly distributed around the circle, then you'd have a phase locking value of 0. Let's get this started though. But before performing the convolution, let's take a look at this Wavelet design tool that I forgot to show in the last video. This tool performs the same function as the script that I showed in the Morlet Wavelet demo, and simply allows you to see how different parameters will shape your wavelet. For example, for this task, I'm mainly interested in the 6 and 15 Hz frequencies, so I'll take a look at those wavelets. Since the oscillations I'm looking for here are stimulus driven, I can expect a very narrow band of activity. So I'll want to define a very narrow wavelet in the frequency domain. But before I just jump into performing a convolution with a half maximum width of 1 Hz, I want to make sure that the time precision isn't going to take too much of a hit. But by plotting these, I see that I have a time domain width of about 900 milliseconds. That is pretty wide, but since the trials are 10 seconds long, I don't actually expect to see sudden changes in time. So this is perfectly fine for this application. So now let's actually do the convolution. I'll define that half maximum width of 1 Hz, and I want to take a look at all frequencies between 2 and 20 Hz. I'll also take the complex signal as the output. But instead of creating almost 40 new datasets, I want to use this last frequency and channel space option that I described in the mu rhythm demo. So I have to pick only one channel, and I'll take IZ since SSVEP activity is usually very localized to that area. And now when I run this, you can see that my EEG data signal is complex valued. However, the data scroll will only plot the real portion of the complex signal, so it'll appear to be bandpassed. And you can see that warning here. Now make sure to be very careful what you attempt to do with your data at this point, since neither EEGLAB or ERPLAB actually know that you're working with complex signals anymore. I've already made sure that the operations that I'll show here are fine though. Our data is set up like this image right now though, with both amplitude and phase information. So the next thing we need to do is normalize our data to be unit vectors. And we can easily do this using the complex data operations tool. This tool allows us to extract information from a complex data set, creating a new data set. So we can take out the phase information and create a real valued phase data set, or bandpassed, power, or amplitude data as well. I'm going to normalize my data though. And so now it is still complex, but all the complex vectors are of unit magnitude. And that puts us at the second step that I described earlier, shown in this image. Similar to the baseline normalization tool that I showed in the mu rhythm demo, the complex data operations tool may seem unnecessary since these are simple mathematical operations that can easily be performed in the command line. But it is nice not to have to switch back and forth between the GUI and a script. Also, actions taken from here will be saved in the EEGLAB and ERPLAB history store, whereas command line actions won't be. So this is good when using the GUI to help build a batch processing script. But now that we have our unit magnitude complex vectors, we can simply use ERPLAB to average together all trials in each bin using the compute averaged ERP function. And we'll name this new ERP set ITPL for intertrial phase locking. Of course, ERPLAB thinks that it is just averaging real valued voltage signals, but when it gives us the new ERP set, that signal is made up of the averaged complex vectors, like the red line shown here. And the magnitude of those vectors are the intertrial phase locking values. So all that's left to do from here is to extract their magnitude. Again, we'll use the complex data operations tool, but this time for ERPLAB data, and we'll extract amplitude. And so now the resulting ERP set contains a real valued signal this time of phase locking values. Of course, remember that rather than channels, we have frequencies in the first dimension of our ERP data signal. So instead of ERPLAB plotting functions, we'll use the frequency by time plotting function included with the time frequency analysis package. And so here we can see very good phase locking at exactly the bands of interest. This top plot shows the phase locking for the 6 Hz trials, where we can see phase consistency at 6 Hz and some at the harmonics. And in fact, these phase locking values are over 0.9 and 0.95 even, which is extremely high phase coherence. And it looks like the same goes for the 15 Hz band and the 15 Hz trial. You can see where the phase locking goes away at 10 seconds when the trial ends, but it actually fades away over the course of maybe 300 milliseconds. It may be possible to entrain your oscillations using flickering stimuli like this that could continue on even after the stimulus has been removed. But I think that here, this is just temporal smearing since we use wavelets with an almost 900 millisecond half maximum width. Of course, just like in the last demo, I've included a script that will duplicate what we just did here, along with step-by-step GUI instructions. And here, if I run this, you see the exact plot that we looked at just a moment ago. Also down here, there's another section of the script that, rather than calculating the phase locking at only channel IZ across so many frequencies, is calculated at just 6 and 15 Hz across all channels, and will plot the time domain head plots using ERPLAB's Scalp map plotting functions. So here in this top window is the 6 Hz phase locking in the 6 Hz trials, and the second window is the 15 Hz phase locking in the 15 Hz trials. And of course, in both cases, this activity is strongly localized over the striate cortex. I won't actually demonstrate calculating this in the GUI though, since it's just a combination of the actions taken in the mu rhythm demo and the demonstration I just gave. Finally, in this third section of the script, I show how the time frequency analysis package can be used to calculate power changes in the same SSVEP dataset. But in addition to power change, which is what I showed in the mu rhythm demo, I also show how to calculate the phase-locked and non-phase-locked power changes, or sometimes called evoked and induced power changes. So in this image, the 6 Hz trials are plotted on the left and the 15 Hz trials are on the right. On top is total power, which is what we would get following the instructions given in the mu rhythm demo. But then we've also separated out the non-phase-locked and phase-locked components. These are the non-phase-locked power changes in the middle plots, which are power changes that happen consistently across trials, but with no consistent phase relationship to the stimulus. And in these bottom plots is the phase-locked power change, which looks very similar to what we saw in the intertrial phase locking analysis, except that this plot is sensitive to both phase and power changes, whereas the phase locking is not sensitive to power changes at all. So of course the 6 and 15 Hz bands show a phase-locked power increase, but I think you can also see a drop in the alpha band power, which only shows in a non-phase-locked event. And this is reasonable since the alpha ERD is probably reflecting the visual stimulation, but there would be no reason to expect that it would be phase-locked to the stimulus. Now, it really turns out not to be practical to calculate induced and evoked power changes using this package within the GUI, but you can take a look through the script to get an idea of how you might do this programmatically. Anyway, that wraps it up for this demo. Hopefully these videos and the demo scripts that are included with the function files will be useful in understanding how to use this time frequency analysis package.